Okay, so sorry for this delayed start of our lecture. So our tablet pencil didn't work, so I just reboot our computer and now it seems work. Okay, so this is the second lecture, or second last lecture of our semester, and this lecture and the last one will be devoted to the small signal analysis. So initially I tried to consider not only this small signal analysis but also some kind of a perturbative analysis. However, so when I prepare my lecture material, I have found that actually there are tons of things to be covered even when we consider small signal analysis. So unfortunately we had to restrict ourselves to only small signal analysis, but that is quite much closely related to other kinds of analysis like sensitivity analysis. So I think that at least this lecture or these lectures can be a good starting point for your further analysis. Then let's go to the frequency response. So now think about this case. Consider a single device PN junction. So we have already covered this device several times, and now let's assume that we have applied 0 volt to its cathode as usual. However, the anode voltage is now assumed to be okay, this is good, better for highlight. Okay, so anode voltage is given as a sum of this DC voltage and sinusoidal time varying voltage. So this one is time independent and this one is time dependent, and you know it can have a very clear frequency component. Only the frequency of F is given to this anode voltage. So we assume a small amplitude of V amplitude. So how small is it? Of course it depends on the situation, but in many cases like 1 millivolt in electronics it seems to be small enough, or 1 microvolt, yes, this is sufficiently small, and 1 nanovolt, of course that is quite small. So you know that when we say small, this is the range of micrometer, a microvolt or millivolt. But you know, for example, 0.1 volt, certainly for these days, this is too large. So don't treat this too large voltage amplitude. Okay, so now this is quite important, an important approximation or assumption. We have small amplitude. Then somebody can say this way, okay, now I think that this will be, for example, 1 microvolt. Then how about this DC volt? Then since this is small, so for example 0 volt, we cannot apply this approach. 1 volt, yes, we can apply this approach or analysis. The answer is no. Even when you have 0 volt or whatever, even minus voltage, you can easily apply to this analysis. So please don't be confused with smallness of your amplitude, time, the amplitude of a small signal variable, and the value of your DC voltage. So it is not related with this smallness of amplitude. Okay, so simply speaking, even when your anode voltage is just 0 volt or 1 microvolt, 1 nanovolt, it is not directly related with your amplitude. So you can just take any value of a DC value. Okay. Then now under this assumption is key. Then now let's try to observe the another current after a long time elapsed. Of course, when you just start the initial time transient, so say that previously you had no sinusoidal signal before t equal to 0. So say this is t equal 0, and before the transient start, we just applied the DC voltage only. And now at time equal 0, we start to apply sinusoidal signal. Then what will happen? For a few time period, there will be the initial transient by the start of this new transient or new sinusoidal signal. So we cannot believe the result of this time period. However, let's say that after 10 periods later, 100 million periods later, then actually it will be diminished, that whether that was sinusoidal or that was just DC, that will be forgotten. So we will just have just stabilized response of our system with respect to this sinusoidal excitation, voltage excitation. So our assumption is, or our consequence obtained from our assumption, small amplitude assumption, is now another current can be also expressed as sum of DC component and AC time dependent component. So now think about the extreme. Let's say that amplitude goes to 0. Then what will happen? Of course, this amplitude of your sine component and cosine component will be diminished, and only remaining term will be the DC term. So DC term can be found even without DC term. Oh, sorry about that. Can be found even without this time-dependent term. However, these quantities are really dependent on the applied voltage. So now think about this one. You have a PN junction. You have applied 0 volt as a DC volt, or minus 0.5 volt as your DC volt, or applied positive 0.5 volt to your DC voltage. Then when you apply small signal, then do you expect the same response of your AC signal? The answer is, depending on the DC operational point, you will have quite much different behavior of your amplitude. So simply speaking, we can think about in this way. In this system, now you can think that here we have certain black box and we apply voltage. Then we have current. Yes, if we apply DC voltage, then you will have DC current. This relation can be found even without any kind of AC signal. However, now think about this one. Your entire input is no longer given by this DC voltage, but also time varying voltage. Then what will happen? Your output current will be also contain what? Also contain DC current and also time varying current. Then you can understand the relation between this time varying voltage and time varying current can be found. An important point is this black box describing the relation between time varying voltage and time varying current is not very much independent. Actually, it is dependent from this DC system. From DC system, we can construct this time varying system or AC system, and that is the major result of our today's lecture. Okay, so let me just come back once again. Then we can write down in this way. Of course, this is also an assumption. So, for example, the natural question is, why do we have only this component and sine component with frequency f and cosine component with frequency f? So I'm just saying that input contains DC and frequency f. So therefore, our system generates also DC and frequency f components. I'm saying in that way. But you know that in order to justify this kind of relation, we must have what? We must have a linear system. If we have a linear system, then it is always true. If you have DC and frequency f component, then that will generate also DC and frequency f component. So my question is, are we assuming that our PN junction is a linear device? So how about your opinion? Please think about IV characteristics of your PN junction you have simulated up to now. Do you think that that is really a linear circuit or linear device? So you can easily remember that when you perform your homework problem accurately, then you will have your anode current is a function of anode voltage, and it shows something like exponential behavior. So certainly this is a non-linear device. No, it's not a linear device. However, right now I'm saying that when we have DC and frequency f component, the output will be also contain only DC and f component, treated as if a linear system. Certainly, it is not a linear system, it is a nonlinear system, but it is treated as a linear system. Why? So you must feel some contradiction in my discussion. So the point is, we have applied this small amplitude approximation. Within this small signal approximation, although the entire system is a non-linear system, but we can build a not linear but linearized system can be found. So that is the point of our today's lecture. I mean that all of our consideration is valid only when we have a small amplitude. When we have a small amplitude, then even for this highly nonlinear system, we can make certain linearization. So although you have a certain function f of x, however, you can always try to build a Taylor expansion. So like that f evaluated at your operating point, and you can say that df over dx times delta x. This is the linear approximation for your any arbitrary function. So when you have delta x, the perturbation which seems to be quite small, then your approximation can be valid. Of course, if you have quite a large delta x value in its magnitude, then it is no longer possible to approximate in this way. You have to consider second order, third order, higher order components. So it is true that as much as your small signal amplitude is remained as small quantities, then we can say that the system can be treated as a linearized system. I'm stressing this lesson quite a lot, so please note that although our discussion up to now seems to be quite fascinating, but please remember that that is a limited theory, so within small amplitude. Okay, so anyway, now let's say that our goal is to calculate this amplitude. Oh, when we apply certain amplitude, voltage amplitude, then what is the sine amplitude and cosine amplitude of our current? That is our goal. Then how can we get the frequency response? The simple and most straightforward way is run a sufficiently long transient simulation. So, of course, as I told you before, the initial response due to very first introducing the time-varying excitation will be diminished after some periods later. Then, after a long time later, for example, your nth period and your n plus 1th period cannot be distinguished anymore because now the system has been stabilized perfectly, so your response is the same between two periods. Okay, so you cannot distinguish whether this is the starting point of nth period or n plus 1th period because the output looks perfectly the same. So now you will have this condition: two neighboring periods that do not show any further differences. Then you can take the one last period, then you can calculate the frequency component. For example, just taking this Fourier transformation, then you can calculate this amplitude for sine and cosine. So please note that when you insert your uh, in the case when your sine your anode current just follows 2 pi ft, the same one, then this integral will give you just half of t, so that will be cancelled out, so you will have the unit amplitude. Simply speaking, if your anode current contains sine 2 pi ft, then the amplitude of your sine component will be generated by this operation. Of course, if your component has other things like I cosine component times cosine 2 pi ft, then you will just have I cosine component. this is the way to pick up the frequency component by applying Fourier transformation. Okay? Actually, this is not Fourier transform, Fourier expansion. Anyway, so now let's have a look at the real application of this kind of approach. So we have applied the DC bias condition of 0.5 volt forward bias condition. Now we have a small electron conduction or electric current conduction, and but still not that much fully turned on. And we have applied a small signal at 1 megahertz. So for this device, 1 megahertz is not that high frequency. And we have observed 10 period. Of course, in its first period or second period, the transient simulation result is not that much stabilized. However, after 10 period later, then I can certainly say that the signal is fully stabilized. You can see that this is the result of a 10 period long signal. Of course, this is just a 10th signal. In order to get this one, we had previously this 9th signal, 9th period, and 8th signal period, blah blah blah. However, we just took the stabilized last result. Okay, so are you with me? So now once we have this form, then we can treat it as a combination of DC component and frequency F component. Then from this one, you can try to calculate DC value. How can you calculate the DC value? So you can just calculate the time average, and you will find that the average is simply given as, yes, this value. Yes, you have a certain this value. And how does it look like? Is it synchronized with a sine signal or cosine signal? If this is time equal to 0, then certainly you can see that this signal is strictly having dominant component like sine component. If we have a cosine like component, then that will look like in this way. Okay, so are you with me? Therefore, we can say that, okay, when we have a sine input for our voltage, then it just generate sine input. Why do we have this sine to sine conversion? It is only because this transistor or this diode in its forward mode. Okay, so now we have applied 0.5 volt, so there is a certain current conduction. So if we slightly increase the voltage, like for example 0.1 millivolt, then there will be a slightly larger current flowing due to this additional voltage. So it means that that will be in phase to your input signal. If you increase your voltage, then depending on the increase of your voltage, you will have a larger current. And if you decrease your voltage, then your current will be also decreased. That is given as your, sine amplitude. Its value is given here. And now you have another one like cosine amplitude. Of course, you can see that its amplitude is smaller than that, but this is a non-negligible value. What is it? You have applied a sine signal, but now you can get a small cosine signal. why do you have this component? In order to understand the reason why we have this cosine component too, let's go to this way. Instead of previous 1 megahertz, now I increase the frequency up to 100 megahertz. Now it is 10 times higher than 1 megahertz. Then please have a look at the response of our anode current. Do you think that this is following still sine component, or do you think that now it is following the cosine component? What is your opinion? Of course, you can see that this one now follows cosine component. Then what happens? Actually, its sine component is not that much changed. So its order is quite similar. So it is just the order of some 10 picoampere. However, now you can see that its cosine component is almost 700 or 760 picoampere when compared with that one at 1 megahertz. Its amplitude is enlarged by a factor of exactly 100. So what do you think? Why do we have the increased cosine amplitude? Exactly following the increase of frequency. It is related with, this is related with time-dependent quantity. And you know that although the system is, the diode is in its fourth mode, however, it still has a capacitive component. And capacitor current can be obtained by I of capacitor current is given by C times dV over dt. So therefore, if we change our voltage 100 times faster, then actually this one will give you 100 times faster, higher value. For example, let's say that V is simply given by sine 2 pi times 1 megahertz times t. This is our previous case. Then our capacitor current can be calculated as C times time derivative of this sine 2 pi ft. So what we will get is just 2 pi times 1 megahertz and cosine 2 pi 1 megahertz and t. That will be what? That will be the current, capacitor current at 1 megahertz. Now let's go to the higher frequency. Instead of this 1 megahertz, now we have 100 megahertz. Then what will happen? Our capacitor current will be given by the same C. However, here instead of 1 megahertz, we will have 100 megahertz. So simply speaking, you know that the capacitor current will directly depend on the frequency. So since we have increased the frequency by factor of 10, by factor of 100, so that's the reason why our cosine amplitude is increased by factor of 100. Okay, so now you understand the behavior of this simple PN diode. So depending on the frequency, the response of your system can be completely different. So that's the reason why actually we must consider all different frequencies. For example, in engineering, if your considered frequency range is given, then you must understand the frequency response of your device or your circuit at those frequencies. Okay, so now let's go to the small signal analysis. So up to now you feel quite satisfied because now by learning a long transient simulation, not only just time dependent behavior but also frequency response of your system can be rigorously calculated. However, in many cases, your role is not just to calculate the frequency response at a given frequency, but please draw the frequency response as a function of frequency. So you must have 1 megahertz, 10 megahertz, 100 megahertz, 1 gigahertz, 10 gigahertz. Then please try to draw your response function. Then how does it look like? You must calculate this one and also calculate this one and calculate this one and also calculate and calculate. So you must consider many different frequencies for your calculation. For example, if you have to calculate from 1 Hz to 100 gigahertz, this is 11 orders of magnitude difference, then you must calculate several. So for example, even when you start from 10 to the 0 to 10 to the 11 and with just one decade for each frequency, then still you must have 12 frequencies. If you spend more, for example, let's say that 1 Hz, 3 Hz, also 10 Hz, 30, 100, 300, in this case, you will have, well, maybe not 12, but you will spend 23 frequency points. Of course, if you want more, then you must have larger number of frequencies and sub-app. Okay, well, anyway, you have to do it, for example, 12 times. Then, now, using our transient capability, now let's try to calculate all kinds of these things. Then how can you do that? First of all, you must prepare a certain DC solution. So DC solution can be calculated only once. You don't have to do it many times. Just to calculate the DC solution and store it. Good. But now you must learn several, how many? So NF times of long transient simulation. After that, after the long transient simulation is over, and take the last simulation result or the last period and make the frequency analysis. So if we have to estimate the computational effort for drawing this single graph, then we can say so. First, we must perform only one single DC calculation. Maybe it is not that much. After that, if we have to calculate 12 times, then we must perform 12 times of single transient calculation. So then, how does it look like? This is single transient calculation. For example, if you have to have 10 periods, and if you have to spend 100 time points per each period, then you know that this one, just to say, you must spend 1000 time points for your single transient calculation. However, you have 12 points, so it means that even for this simple case, you must spend 12,000 time points to calculate the frequency response of your system. Are you with me? So do you think that this is reasonable or not? Of course, I wanted to say that which one is reasonable or not really depends on the situation. For example, if you are working not this frequency response, but also the real time-dependent quantities, then you must spend your computational effort. For example, if you are working with write and erase of your memory cells, then you must actually perform this kind of a full transient one. However, what we are doing right now is not the full swing of your device, but it is just says that what happens if we have a certain DC point and slightly changing the voltage, and what will be the response. This is just a tiny problem compared with this rail to rail swing of our more general problem. So now we can try to, for this specific case, for this small signal case, we can try to find out much more efficient way. So here we have an inefficient approach. Can we avoid the time-consuming transient calculation to obtain the frequency response, or sorry about that, response quickly? And the answer is yes, we can. How can you do that? We don't know right now, but let's assume that that is possible. Then, in this efficient approach, the computational efforts can be expressed as the same DC calculation. This is done only once, and now single frequency calculation is much more efficient than this single transient calculation. So now the effort can be reduced significantly. So how much is more efficient than this single transient calculation? So now think about this one. In order to calculate this single transient calculation, we must perform, for example, 10 period, and inside one period, a single period, we have introduced 100 time points, and in order to solve each time point, so we must, for example, so of course, since we have applied quite a small voltage changes, so it can take just, for example, let's say only 2 Newton iterations for this one, each point. So this is quite much idealized one. So now we will have single transient calculation will take, in this simple case, 2000 Newton iterations, not time points, but 2000 Newton iterations. And I wanted to say that single frequency calculation can be done only 1 Newton iteration. Then please try to estimate the efficiency gain obtained from this full transient simulation and single frequency calculation. You can see that actually when we make a comparison between these two efforts, actually this single DC calculation doesn't play much role, because this is not that high. Actually, I wanted to say that in this efficient frequency domain one, we cannot neglect it because this is considerable. However, in the case of our inefficient time transient case, actually we can neglect it because it takes too long time. But now, in our case, now since only one Newton iteration is required for the calculation, the reduction factor will be quite close to almost 2000 if we neglect the contribution from single DC calculation. So I wanted to say that in this case, actually the limiting factor is no longer given by this frequency calculation. Compared with this single DC calculation, actually this one takes even higher computational burden. So simply speaking, frequency calculation comes almost free without much additional computational effort. So it sounds a little bit weird. How can you achieve such kind of a huge improvement when we say just efficient way? But please believe me, and from now on I will explain how can you achieve such kind of drastic improvement in its efficiency. But of course, I wanted to say once again, this efficient approach can be justified only when we have small amplitude approximation. Without this small amplitude approximation, all of our current discussion is invalid, so we cannot apply our approach to the general case. Please note that we must apply this one to the limited case. However, where can you find it, or where can you find the major application of this kind of thing? If you are working with RF device, then actually this is the very important point. The point you must care is just the frequency response of your transistors. Then in this case, your frequency domain calculation capability gives you the real boost for your computational efficiency. Okay, so do you have any question up to now? So if you have any question, then please let me know. Okay, so if you don't have and if you don't have any question, then I will just go. So today I have stressed so many times about the importance of this assumption, smallness of our time varying quantities. So then in any case, actually generally we can write down in this way. Our physical quantities can be decomposed into its time-independent quantity called DC quantity and time-dependent quantity. Yes, this is time-varying quantity. And we wanted to say that, okay, of course it is time varying, so actually it is a time dependent one, but we can say that when we take the peak to peak value of this variation or peak to peak value of this variation, we will say that these are small in some sense. Okay, well, once again, you may say that, okay, professor, if we have zero voltage, zero DC voltage, yes, then we have applied voltage, small voltage, 1 millivolt amplitude. Then compared with this zero voltage, even this 1 millivolt is higher. So is it applicable or not? As I told you before, still in this case you can say so. So please don't try to make a comparison make a comparison between UDC and small quantity. No, so please think about just the smallness of your time varying quantity. And under this assumption, we can write our drift diffusion model in this way. What is it? I just insert the form, decomposed form, into our Poisson equation. And this is electron continuity equation. And this is whole continuity equation. What is new? There is nothing new. I just write down in a given way. This is just Q times P, and this is just minus Q times N, and this is nothing but epsilon times gradient of our electrostatic potential. And you know, this is just electron current density. This is whole current density. And here we must calculate round n over round t, but since ndc is a dc component, it does not contribute at all. So we will have only the time derivative of delta n here instead of partial derivative of ndc over with respect to the time. So that is not shown here. So of course, this continuity equation is hiding very important one here. What is the exact form of this delta Jn and delta Jp? That is hidden. And please remember that Jn, Jp can be expressed as a sum of drift and diffusion. And with time varying variables, we can write them in this form. How can you do that? So please just add here ndc plus delta n. Please add phi dc plus delta phi and just evaluate it. Then you will find that ndc times delta phi, delta n times phi dc. Maybe you may ask me this question, or if we do so, then we must have something like a delta n gradient delta phi. Why we don't have this term? Because this is a second order term. So this is small and this is small. So both of them are small. So compared with this linear term with respect to the small quantities, then this is too small. So we just neglect this second order quantities. So even with these second order quantities, it seems to be quite complicated. Yes, but anyway, this is the form. And of course, since we have implemented the Shapeto-Gummel scheme for our DC simulation, actually we do not explicitly use this delta Jn and delta Jp. Just to first consider the form of the discretized form, Shapeto-Gummel discretization form. After that, introduce small changes in your electron density and your potential. That will give you the discretized version of delta Jn and delta Jp. Okay, so are you with me? So please do not try to explicitly calculate following in this way. Instead of that, what you have to do is, since Jn is simply given by, for example, Q times dn over delta x times ni plus 1 Bernoulli something minus ni Bernoulli minus something. So in this case, if you wanted to calculate delta Jn, then please insert delta here or delta here, or delta here or delta here. Then you will have the form of delta Jn, not directly from this analytic expression. So are you with me? So in principle, yes, you can calculate the current densities and its small signal version. So please note that now let's come back to our previous discussion. Anyhow, now you understand the form of delta Jn and delta Jp. Now this is the equation. These are the equations you must solve when you consider the case including small signal voltage excitation. But your observation now goes in this way. Here, let's have a look at here. You have some quantities like phi dc, n dc, and p dc. These are solutions of your DC problem. How do you solve your DC problem? In order to solve your DC problem, you satisfy this one. Divergence of epsilon of gradient of your phi DC and q PDC and minus q NDC and time plus q doping density equal to 0. Your solutions satisfies some of these left-hand side terms vanishes. Also, in the case of your DC current, your DC current density, its divergence vanishes. Also, divergence of your JPDC vanishes. So, now you can say that actually these components, when they are summed, they vanish. Also, this one vanish. So simply speaking, in other words, if we just neglect the terms from DC contribution, now you can say that actually the equation only for small signal or only for time varying quantities are simply given by in this way. Please note that here we don't have a explicit dependence on your phi DC, NDC, and PDC. They are hidden. Where can you find its dependence? Actually, you can find its dependence on DC solution here and there. Please, delta Jn, delta Jp, both of them contains the dependence on NDC and phi DC. Therefore, this delta Jn and delta Jp are actually dependent on your DC solution. However, anyway, this is the compact form for your small signal variables, time varying components. So the way is like this. Once you get the solution, first solve the DC solution. Then from DC solution, you can construct this AC system. This is the set of equations where delta phi, delta n, and delta p are unknown variables. You can directly construct this system and solve this system. Then you will get potential perturbation and electron density fluctuation and hole density fluctuation. You will get these time varying quantities. Okay. Then how can you actually calculate it, or how can you actually construct this AC system? I think that is the main beauty of today's talk. Up to now, maybe all of you are following me. But point is, if constructing this AC system is too tedious and time consuming, then that is not that much beneficial. But the main beauty comes from this one. This AC system can be directly obtained from already constructed Jacobian matrix. This is the real observation. Okay, we wanted to build a system where fluctuating quantities are involved, and that is actually quite similar to the Jacobian matrix. Let's have a look at it. The linearized system, the system for our AC component or time-varying component, is closely related to the Jacobian matrix. So please consider this one. We always solve this AX equal to B. Then A is Jacobian and X is the update delta X, the solution of it. Then how does it look like? Actually, you can find that the Jacobian matrix multiplied by our update vector just to describe this way and this way and that way. You can easily understand. So simply speaking, our DC Jacobian matrix we are constructing every time is related to the small signal analysis at the zero frequency. Why we say zero frequency? Because you know this is nothing but AX, A times X, and our AC signal or our AC system should satisfy this functional form. So please try to make a comparison. So I will just zoom out them for better comparison. So please try to make a comparison between our AC system shown here and our DC Jacobian system. What is the difference between them? Actually, when you compare this Poisson equation, there is no difference between them. A Poisson equation can be perfectly, AC Poisson equation can be perfectly described by our DC Jacobian matrix. However, in the case of electron continuity and hole continuity, we have a time-dependent term, and that is not covered by our DC case. So if we have zero frequency or quite a low frequency case, then this time-dependent term or time derivative term can be really negligible. In this limit, we find that DC Jacobian matrix is closely related to the AC system. Okay, of course, we must consider these two terms separately for non-zero frequency case. Okay, so in the case of non-zero frequency, how can we do that? In the case of non-zero frequency, we assume that the time dependence of exponential j omega t. So exponential j omega t. So if you are coming from the physics department, then maybe you are more familiar with the time stamp like exponential minus I omega t. But in the engineering part, we prefer to have this positive convention. So I will just follow this positive convention. So this is the assumed time dependence stamp. Then when we say delta n, actually we say that this is the time dependent form of our quantity. Okay. After that, let's try to get the time derivative. Then what happens? Please note that this delta n is no longer time dependent one because all of its time dependency is described by this assumed exponential j omega t. So when we take the time derivative, it will simply give us j omega exponential j omega t. Of course, once again, this exponential j omega t is always understood. So we are not talking delta n times the exponential j omega t because this one is just understood. Therefore, we will just neglect this one too. So simply speaking, our time dependent term go into this way, and we will just say that okay, this is corresponding to delta n times j omega. So in the frequency domain, so linearized system, our linearized system now becomes all taken from just our DC Jacobian matrix. Please reuse your last DC Jacobian. After that, just add this time dependent quantity, then solve at a given frequency. Well, then how can you change your frequency? Well, please reuse it just to increase your frequency. Then you will get different frequency response. So this is just one solution of AX equal to B system. So that's the reason why I told you that in this efficient implementation, the cost of single frequency calculation is equal to that of 1 Newton iteration. So is actually at the first glance it is hard to believe such kind of thing because it is too much more efficient than our transient simulation. But please note that this kind of amazing achievement was obtained with significant approximate assumption. Small signal, a small amplitude. Once we adopt this small amplitude approximation, then things can be drastically simplified. We have shown up to now. Okay, so do you have any question on today's lecture contents? So today I just told you approximation and the derivation and something like that. And in our last lecture, lecture 26, I will show you some real application of our program. Then you will find some feelings about the AC analysis. Okay, do you have any question? No? Okay, then although this is not an official homework, so I wanted to strongly recommend you to implement it by your own. You know, the real implementation is not that difficult. First of all, don't consider frequency component. Just consider the low frequency limit. In the low frequency limit, actually you have the Jacobian matrix. Then you can just solve this Jacobian matrix once again. It is your everyday job, so it is not that difficult. The point is, what is the meaningful system for your AC system? So up to now, we have shown that we can reuse the Jacobian matrix. However, we never talk about the residue vector B. What should be the form of our B vector? That will be covered in the next lecture, and I will show you the result. Okay, if you don't have any question, then I want to wrap up today's lecture. Thank you for your attention.